Test, test, test. Hey Laura, can you hear me? Hello? Hey Laura, can you hear me? Hey Laura?
Hello?
Hey Laura, can you hear me?
Hello?
Hey Laura, can
Oops.
you hear me?
Yes, I can hear you from my
Okay.
computer.
All right. So I was trying to call you. I'm here. So I can hear you now. I'm all set. So hopefully you can hear me, but it's more important that I hear you. Thank you.
Okay, cool. Yes. I think everyone's here now. We should just go ahead and start. Okay. Okay, so hi everyone, so I'll stand and just hi everyone, welcome to my preliminary exam. I would like to thank my advisor Ming Lin, my committee members Dinesh Minocha and Professor Tom Goldstein, as well as friends and family joining in person and online. Yeah, go ahead and start this. Yeah, so for those of you who drive regularly, I'm sure this map isn't new to us. Anyone who drives on 495 knows that traffic congestion is almost never clears up until late night. So factoring additional time onto routes to account for congestion is quite normal if we live in this area, at least for those of us who might commute to and from Montgomery County or Virginia. So when we look at the societal cost for something as mundane as traffic congestion, it comes out to be pretty high for individual people. TRIP, which is a transportation research nonprofit, estimates that the average motorist in the Maryland, DC suburbs lose about 86 hours and nearly $2.2 thousand a year on traffic congestion alone as of 2024. So when you sum this up to account for the entire population, the cost can reach the billions. So here's an overview of where we currently stand in commercial products with respect to progress towards autonomous driving. And since 2014, we've made steady progress in advancing from L2 to L4 autonomy, with several products and services hitting the market for commercial use. And the rate of progress has been extremely exciting, especially since autonomous driving can offer prospects in reduced traffic accidents and congestion. But even though it seems like we could hit L5 anytime now, the gap between L4 and L5 is also arguably one of the hardest to close. So if you can remember, L5 was the level where autonomous policies can be entirely unsupervised by humans. And this means that the policy should be able to reason with unforeseen scenarios and complex decisions. So the trend in autonomous driving research and commercial products is typically to scale for better performance, especially for the fringe case scenarios. So if we have rainy weather, complicated roads, or left-handed driving, the easy solution is just to collect more data. But what happens when we have data that we don't want occurring in the real world whatsoever, like car accidents? Sure, we'll have some data that might be collected naturally, but is this something that we really want to scale up in data collection? So the question is data and scale really all we need? There's many cases where we cannot collect more special case data without collecting massive amounts of average case data in the first place. And another problem is that human factors like driving style aren't even measurable yet. So in terms of like a quantifiable number. So the challenge with human factors will become increasingly important as we transition into mixed autonomy traffic. So what is mixed autonomy? It describes traffic that is partially human-driven and partially automated. Since we still don't know how people behave around autonomous vehicles, it's difficult to tell how traffic will change when we mix in autonomous vehicles. This aspect of traffic sim is difficult because behavior is somewhat abstract and difficult to define. It's not some quantifiable value that we can observe from the traffic state and directly pump into a vector form. So traffic dynamics, on the other hand, operates with much higher rigidity on several levels. So on the high level, we have global traffic flow. And traffic sim models include both macroscopic models, which treat traffic like a fluid, and microscopic models, which are agent-based and describe acceleration of individual vehicles. And on the low level, we have vehicle dynamics, which describe how a vehicle moves as a robot. So the problem is that current learning-driven traffic models do not consider even vehicle kinematics, which produce trajectories that may not even be physically feasible. Ultimately, in contrast to the human factors discussed before, traffic dynamics are rigid and describe traffic systems well enough without fancy neural networks. So we just discussed two different aspects of traffic modeling, which vary in rigidity and the human factors and traffic dynamics. Here we discuss general challenges in autonomous driving that prevent policies from being deployed with full unsupervised autonomy. Really, it's just any scenario that strays farther from the low density, sunny, and clear weather case. So this includes limited visibility, risky scenarios, or overly aggressive and overly anxious drivers. So this brings me to my thesis statement, which is combining differentiable traffic dynamics, human behavior priors, and visual perception robustness with deep learning can not only provide improved performance on the general case, but also improve interpretability, data efficiency, and robustness on rare events and cases. So this thesis statement can be broken down into three categories. The first one being the differentiable models of traffic and vehicle dynamics. So this is the aspect that's rigid and already work for most cases with these simple mathematical models. And we want to model these differentiably and explicitly to prevent the relearning of the wheel with these high dimensional neural networks with high levels of expressivity. So second, we have the human factor studies, which represent non-rigid concepts that are understood very little and not easily quantifiable. And lastly, we have analysis of sensitivity to natural corruptions, which account for the edge cases not related to the traffic state. So based on the challenges discussed in previous slides, here's my research roadmap. In the first two works, I investigate modeling and integration of high-level traffic dynamics in autonomous driving, which represent the rigid concepts, as well as the low-level vehicle dynamics. In the other two works, in blue, I investigate the modeling of non-rigid human factors like driving style with two approaches, one with a user study and one as a latent variable. Then in purple, I investigate modeling sensitivity to noises to combat natural corruptions. And finally, the plan is to render the generated novel behavior from previous works as first-person observations, which will bring my work full circle to link observed novel scenarios and sensor observations. So now I'm going to present the first work on integrating high-level traffic dynamics. Basically, we seek to answer the question, how do we apply learning from mixed autonomy problems to autonomous driving policies? So given driving sensor data and its paired local traffic state, can we improve global objectives for all vehicles in the traffic system? After all, improving the entire system also benefits the individual in the sense that we get to point A to point B faster. The challenges are that we don't have this pairing in the first place, so it's difficult to evaluate the effect of AV actions on the traffic system in a closed-loop fashion. So in this work, traffic-aware autonomous driving with differentiable traffic sim, we present one of the first methods which unify the benefits of mixed autonomy traffic optimization research and end-to-end driving policies. And this was published at ICRA 2023. We propose to do this in two phases. In phase one, we learn how to accelerate. This agent learns via on-policy reinforcement learning methods in the Carla driving simulator environment and is rewarded based on improvement of global objectives for the entire traffic system. The acceleration agent provides acceleration actions, while another expert agent provides steering commands. These actions are then executed within a co-simulated Carla and traffic environment. This co-simulated integration is a useful engineering contribution of this work, as this is a key portion that provides the mapping between sensor data and traffic state. Then in phase 2, the acceleration agent directly supervises the acceleration controls of a driving policy, while the rest of the controls, such as steering, is supervised by an offline dataset. So notice that the method for driving policy learning is easily interchangeable with other methods, as long as the acceleration can be separately supervised by phase 1 acceleration agent. So these boxes are left vague on purpose and can be interchangeable. In our experiments, we use a baseline called learning by cheating. In addition, we improve sample efficiency in phase 1 with traffic gradients. So intuitively, traffic gradients are the change from one state to the next across time in a traffic simulation. For example, it describes how a vehicle's current position is related to its own position in the last state or the position of a nearby vehicle in the last state. If we know exactly how vehicles move in the current time step with respect to the last state, we also know how changing the action can change the resulting environments, and then eventually how the action can change the resulting reward. So now we can pick some augmented action, which has a slightly higher reward, since we know how action relates to the reward via the differentiable environment. So here are some results on how sample efficiency improves learning outcomes for phase 1, where TRPO, which is our baseline, is in blue, and diff-TRPO graph, the suffix 01, 02, and 04 are suffixes corresponding to the hyperparameter settings of the threshold value, which determines acceptable action augmentations. When the threshold is higher, it means that we can include actions with greater approximated reward, but it also runs a risk of overshooting the gradient, kind of like single steps in gradient descent. So here we visualize the last results with a traffic simulation on a figure 8 network. So on the left, you can see that the ego vehicle becomes stuck in an inoptimal policy that has all the vehicles moving very slowly at a constant speed, such that no vehicles interact at the intersection. And this is kind of like the naive solution, where you just have the front vehicle holding up all the vehicles and moving slowly. It gets stuck at the top. But on the right, the ego vehicle moves fast enough to control throughput in the intersection. So here's a comparison for average velocity and fuel consumption across Carla test scenarios, which is 26 in total. And across most scenarios, our method in blue consistently improves local traffic flow around the autonomous vehicle in the same lane, while still maintaining similar fuel consumption despite the inverse relationship between acceleration and fuel usage. So in this bottom graph, it's actually a good thing that ours has approximately the same fuel consumption as the baseline, because we might expect that higher speeds increase the fuel consumption as well. So here's a qualitative visualization of scenario 1 from the Carla benchmark. And we show this example as a failure case of the baseline model due to a poor acceleration policy. So the main difference between the baseline and ours is that the baseline learns steering and acceleration jointly from sensor observations, while ours learns acceleration separately in phase 1. And we believe this baseline behavior occurs due to overfitting of slow acceleration or stopping behavior due to the prevalence of stoplights in the offline dataset. The offline dataset is collected with the Carla Autopilot Expert, which drives extremely slow, but this is very common especially in end-to-end driving works that use Carla. So from our results, the key takeaways is that 1, our proposed method separates the learning of driving policy into 2 phases, where the first phase model supervises acceleration predictions, of the second phase via distillation. 2, results show improved global objectives like traffic flow, in addition to fulfilling individual objectives of autonomous driving. And lastly, this complements existing work in autonomous driving, since the learning backbone of phase 2 is modular and can be swapped out. So this work has a couple limitations. The first one being that Current traffic simulators are non-parallelized and unoptimized for learning tasks, at least at the time of this work. So phase one can take extremely long to train. A lot of reinforcement learning environments can run many different rollouts, but in this case, because Carla runs in real time, one episode takes a long time. So I think the phase one took about a week to train. So this is a limitation of current software. The second one is that existing benchmarks in autonomous driving do not consider difficult traffic flow tasks. So what I mean by this is that the Carla benchmark scenarios that I mentioned earlier are not exactly meant for reducing traffic congestion, for example. So the density of traffic is pretty low, and so that might undermine the effects of our method. Next, I'll talk about the low-level traffic dynamics in autonomous driving. So in this work, deep stochastic kinematic models for probabilistic motion forecasting in traffic, we investigate how to use time integration of kinematic models in probabilistic settings. The long title is a playoff of a previous work, which presented the deterministic version. And this is a joint work between our lab and Kitware, and it was published recently at IROS 2024. So before we jump in, I want to explain that there are two ways to model trajectories in trajectory prediction tasks. The first way is in a one-shot fashion, where we predict all future states at once, given the past states and historical context. And this is cheaper to learn and works well in most cases, but this might enable anti-causal reasoning, and resulting predictions ignore the states of nearby vehicles at corresponding time steps. And by anti-causal reasoning, it may produce some sort of reasoning that backwards in time, something like that, where it's not one time step after the next. The second way is an autoregressive style, where we predict only the state at the current time step, given the previous state in historical context. So the good thing about this is that it's naturally temporally causal, which means that one time step depends on the next and has limited information about the future. But this is expensive to learn and achieves similar results on benchmarks compared to one-shot approaches. So in this work, we use one-shot methods for evaluation, but again, we want to emphasize that this work can be applied to both paradigms. We just use one-shot for evaluation. So here we want to enforce causality and feasibility in general for trajectory modeling. This is pretty simple, actually. We just have to roll out the trajectories via the system that they were produced. AKA, instead of predicting trajectories directly, so like history in and then future out in terms of XYZ, we should instead predict the parameters of the kinematic model and then roll them out with time integration. So in this way, every trajectory that we produce from the model is kinematically feasible. But isn't this kind of low-hanging fruit? So the question is, why has no one already done this? It seems a little obvious that we should be using these models automatically. But the problem is that state-of-the-art models are probabilistic now and use Gaussian mixtures and predictions. So this use of kinematic models has sort of phased out, and they were previously used deterministically. The question here is how variance and uncertainty roll out with respect to the bicycle model, which is the kinematic model we use for vehicles. So in a nutshell, our goal is to analytically convert predicted Gaussians of speeds or accelerations into positions. However, the transformations aren't linear, especially if we roll them out with time integration. And previous work usually delegates the covariance matrix of the predicted Gaussian to be learnable, if they were to apply to probabilistic settings. So in this work, we explore several analytical formulations of variance with kinematic priors and see how they perform on Motion Transformer, which is a state-of-the-art probabilistic one-shot trajectory prediction model. It's also the best model that works that's open source. So the methodology is simple. At the core of the math, we just use linear approximations of sine, cosine, and tangent to convert Gaussians of actions into Gaussians of positions. And since the transformations are linearly approximated, the resulting positional distributions are also Gaussian. And the computation is simple and differentiable, and it's also agnostic to other details of the learning framework. So this is, you can really just apply this to any method that uses, that models trajectories probabilistically. And previous works like multipath and DKM, which was the deterministic version that this work was branching off of, have done so in the deterministic case, but neglect the variance portion. So in ours, we show how analytically estimating the variance impacts performance. There's a lot going on the right side of the slide, but really the point is to emphasize that this is all that really, all the implementation really is. So given that you have some sort of distribution of actions, this basically just converts it to positions. And as long as you can convert these into code, this essentially implements the contribution of the work, which is a neat reference. So in our experiments, we use Motion Transformer as the backbone architecture and the Waymo Open Motion dataset for evaluation. And the task is that given a 1 second history, predict the next 8 seconds for a set of traffic agents. So we compared to the vanilla Motion Transformer model, as well as DKM with uniform variance and DKM with learnable variance in all 4 kinematic formulations. And from our results, we observed that formulation 3 provides a boost in performance when we use 100% of the training set for Waymo dataset, which is very large. I think it's 1 terabyte of trajectories. And formulation 2 gives us the most benefit in performance with smaller datasets. Lastly, formulation 4, which uses acceleration and steering, is not only most robust to small perturbations at test time, but also fastest to converge during training. And on the right, we show how qualitative results for formulation 4, when trained on only 1% of the Waymo Open Motion dataset. And the standard deviation value sigma is not only stably increasing across time steps, but also provides the smooth trajectory prediction. So with little to no additional compute, all we do is change how the predictions are rolled out. We hope that future work can apply these computations for probabilistic models to boost performance and convergence. This is also extremely applicable in any setting that uses probabilistic trajectories. So in the next 2 works, we look at human factors from 2 different approaches. The first is modeling behavior directly from humans with user studies. So this is where we have access to the humans and we can directly query them for their driving style and then have them drive in a simulated environment to record their trajectories. This is kind of the most direct approach to getting the pairing between their behavior and their trajectory. But the question is how do we design an effective study that provides enough immersion to produce realistic driving behavior? We can't always guarantee that people are going to drive the same way in VR. And secondly, we investigate behavior as a latent variable from existing data sets. So in this approach, we don't have access to the humans whose data is recorded in the data set. We use modeling techniques to extract driving style as a variable based on their actions over time. So first, I'm going to discuss the investigation of human factors from the immersive VR simulation angle. So why do we want to study behavior through virtual reality in the first place? Why not just put someone in a real car? So our goal is to investigate the mapping between human behavior and driving trajectories. And driving style is arguably the most useful in edge case scenarios. After all, why should we worry about these extra variables in the easy cases? We already can drive in the easy cases without human supervision. So the question is, how do we get driving style to edge case trajectory pairings? This pairing is what's difficult. This isn't feasible in the real world. So our answer is to investigate this with immersive simulations and also benchmark how immersive these simulations are for realistic behavior. So next, I'm going to present our work, a first work on studying human factors with user studies. And this work was a massive effort with several other students and was one of the first looking at driving style in pre-crash scenarios, especially with trajectories. So this work involved the pilot stage before we went fully into data collection. And there's very little work investigating virtual reality for data collection. We found exactly 1 work that mentioned it, and it was a short paper. And we had a series of pilot users help us determine optimal simulation settings for maximal immersion. Then we conducted the data collection stage once simulation design was finalized, collecting both sensor data, driving style annotations, and immersion evaluations. In total for this first study, we had 24 participants, most of which were recruited from the local UMD CS department population through physical flyers and digital advertisements. So in the first stage of the study, we had users fill a questionnaire with a briefing, consent form, simulated sickness benchmark, and a driving style questionnaire. This questionnaire is called the Multidimensional Driving Style Inventory, or the MDSI. And it's a well-validated driving style questionnaire that's used in traffic psychology literature since the 2000s. In the second stage, we put the users through a permutation of 4 scenarios, which we'll show in the following video. Yeah, so this was our setup. This was the very first user study we ran. And as you can see, we were on a budget. But the main idea here was a preliminary exploration of seeing how we can use virtual reality simulations to collect data and whether that data would be valid. This is also the Carla autopilot policy, expert policy, which was used to collect data in the first work. So as you can see, the driving is pretty slow here for the expert. After we conducted the study, we first examined whether the assessed MDSI styles correlate with the actual driven trajectories. So we test Pearson correlation between MDSI scores, which are scalars for each of the 8 factors, and cumulative changes in steering, throttle, and braking, in addition to curvature metrics. And from the results, we noticed that the patient driving has stronger correlations to control input changes, and angry driving has higher correlation to curvature analysis. But surprisingly, though, the correlation for a lot of the factors are not significant enough to in other MDSI factors, which might suggest that the relationship between driving style and trajectory are more complex than linear relationships with trajectory phenotypes. So we then try a small experiment with this data that we've collected with a 2-layer multi-layer perceptron, where the MLP is overfitted on each scenario to predict the driving style vector given a particular trajectory. So in these plots, we color the parts of the trajectory which are most important to driving style classification. In other words, these are the most salient parts of the trajectory with respect to driving style. So interestingly enough, the salient regions are more structured when there's a direct stressor in the scenario, such as the jaywalking pedestrian. So we marked it with the horizontal line on the left. And in cases where there's generic driving, such as the control scenario on the right, saliency is pretty uniform. And so this might further strengthen our suspicion that driving style is an increasingly important variable for edge case scenarios where there's a risk. And so this also aligns with findings from previous work studying the general adaptation syndrome, which is a physiological stress response in crowd simulation. So here's some metrics on the immersion evaluation for this study. And note that all participants in the study have a driver's license. 79% of participants reported high levels of immersion, while 7% experienced severe simulated sickness. We do note that the people who experienced simulated sickness did experience it to quite an extreme degree. So this was kind of interesting to us. And some interesting qualitative observations is that some participants instinctively grasp for controls, which did not physically exist, and very few noticed bumps placed on the highway in scenario 2. So this leads us to interpret the data for scenario 2 more like a control, and that most participants did not use the built-in mirrors, which might be a hint on degraded realism. Just assuming that more people use mirrors in real life to drive, hopefully. So most limitations of this work stem from hardware and software limitations, especially on the simulated sickness aspect. There is very little we could do about the hardware, of course, but the software was also difficult to modify. This reduces our ability to properly improve the frame rate and diversify scenarios. The other thing to note is that the traffic sim was not realistic. Again, this was contingent on the Carla autopilot expert. So the traffic sim was not very realistic at all. And as a direct extension of this work, with the help of a great team of students, we created a new virtual reality traffic simulator for data collection from scratch in Unity, which integrates both virtual reality optimizations in addition to Sumo Traffic Sim, which is similar to the co-simulation from the first work that I presented. And this simulator has expanded the total number of scenarios in the user study to 8, all of which are based on the National Highway Transportation Safety Administration pre-crash scenario report. So we conducted another user study to compare this simulator to the last simulator from the first one, and we saw good improvements across realism, ease of use, and overall user experience. So this was pretty neat, and it was a very obvious improvement in terms of experience. And another byproduct of the simulator is the addition of a larger data set. So yet again, we conducted another user study with 100 participants this time, similar to the first one that we did, except we scaled it up and we recruited everyone else in the same fashion. And this data set includes the Sumo traffic state annotations, sensor data, and simulator replay logs in case we wanted to add more sensors post hoc and go back and reflect the data. In addition to the driving style annotations from the MDSI that we originally wanted to get. So this data set will be released to the public on our project website, and it'll be presented at ICRA 2025. So next, let's take a look at the other approach for modeling driving style, but now with latent variables. So now I'm going to explain what we're doing with parameter efficient persona conditioning for traffic sim. And just another note is that this project is ongoing, but we have some interesting preliminary results which we can share here, and also explain our approach. So what variables influence a driver's trajectory? Prediction is usually conditioned on several different variables to describe the multimodality of future outcomes. So what describes future outcomes? Well, first, we might imagine that where the driver wants to end up, which we call intent, is one factor. And we might also imagine that the surrounding traffic and road layout is also a factor, and we will call this context, just broadly. So in this example, let's say we want to change lane to the top lane. The presence of the two green vehicles split the lane change behavior into two different outcomes. One is lane changing behind the vehicles or deciding to lane change in front. In the context of distance metrics, this discrepancy matters a lot. It's measured in meters over time. However, neither outcome is technically wrong given the intent. So if we don't account for this difference, one over the other may produce large error or lower performance in terms of benchmark metrics, even though both are valid. So currently there's no variable in current works that describe this discrepancy, even though intent and context are the same, the outcome is much different in benchmark metrics. We hypothesize that this difference in outcomes is best described as driving style. So that is, if we account for the intent and context, the variation in outcomes can be then modeled by a latent third variable, which is driving style. And so that brings us to the goal of this work, which is to be able to model driving style with interpretability and controllability for traffic sim. And we want to be able to choose outcomes in this same scenario under different styles. So if we just tweak the style parameter, we can condition the output to be a different outcome. This means that we shouldn't use an uninterpretable high-dimensional latent vector representation for driving style. So like you might do with VAEs, a lot of latent variable modeling involves high-dimensional vectors. We don't want this. We want it to be as interpretable as possible and as controllable as possible. And we also want efficiency without losing base model performance. So since our task here is learning a latent variable, we also run the risk of losing the original model performance on trajectory prediction benchmarks. And lastly, we also want this information to be useful for the generation of novel scenarios using existing real-world logs. So this allows for greater evaluation value of rare scenarios when they occur naturally in the real world. We can use a naturally occurring close call replay log from the real world to generate many different realistic outcomes with different behaviors. So this is our proposed framework for achieving this goal. And the main contribution is on the top half of this diagram. So first we use context embeddings to learn a latent variable. So we just have a latent variable classifier. And in this case, we're starting out with having latent variable be discrete integers. So here we predict a discrete latent variable value to select an acceleration scaling factor. And then we use the sampled latent value to also select an adapter, which we're using LoRa modules, low-ranking adapter modules, for efficient fine-tuning of the decoder. These adapters are learned jointly, so they're not learned in a separate offline process like how they're usually done in multitask learning. And although this work is ongoing, we see some promising qualitative results when visualizing rollouts with different style values. So the ego agent in these samples is actually the light green car, not the dark green car that's centered on. We focus the visualization on this car just to visualize differences between outcomes more easily. So here, the P's on top of each visualization correspond to the probability in the prior that we give in latent variable modeling. So as you can see on the right, we see some edge case behavior where the vehicle accelerates very quickly and changes lane. And this is associated with the prior value of 10% probability. So this is quite interesting. And this was entirely emergent behavior from the training process. So we're planning to wrap up and submit this work to NeurIPS in May once we conduct more extensive experiments. So this work is ongoing, but hopefully should be wrapping up in the next couple months. And the last work I'll discuss here is our work on modeling sensitivity to natural corruptions. And this project was joint work between our group and the Army Research Lab, our PI there being Andre Harris. So this project is well motivated in that we always want to make sure that perception models are robust to natural corruptions. And natural corruptions are a type of noise that are naturally occurring in contrast to adversarial noises that might be learned through optimization. So far, the greatest robustness boosts for perception typically come from improvements in architecture design and foundation models that are trained through shear scale. However, these models are still susceptible to performance degradation when you fine-tune on downstream tasks, especially if the target dataset is small. And this is often the case with practical deployment. So in this work, we propose an efficient adaptive sensitivity analysis method, and then we apply it with a data augmentation scheme to improve the robustness of pixel-based segmentation, and then evaluate on unseen synthetic scenarios in naturally collected samples. In sensitivity analysis, we measure the sensitivity of the neural network performance with respect to the perturbations in the input data. So in other words, we want to measure the change in accuracy over the change in noise. We want to do this so that we can sample uniformly difficult noises to strengthen the model. It could be that a model is robust to noises up to a certain threshold, and where performance rapidly degrades above that threshold. In this case, we want to solve for those uniformly difficult cases to maintain robustness on easy cases, but also include augmentations from hard cases relative to model sensitivity. In that augmentation sampled from uniformly from the augmentation space may not necessarily equate to being uniformly difficult for the model. So previous work has shown that this works, but it's not very practical due to expensive computational and storage constraints. So sensitivity is expensive to evaluate since it's a function of model performance. And one useful thing is that we can leverage is that a neural network trained on generic data X will produce approximately monotonically decreasing accuracy as we increase the noise on this. So in our approach, we find uniformly difficult noise intensities, alpha I, by solving for specific values along a given function G, which is a function of mean accuracy and kernel inception distance between augmented and clean data. So intuitively, G is a function of model sensitivity with respect to noise. To get uniformly difficult noise intensities, we estimate the curve describing G and then approximate the augmentation intensities with that curve. So this process is iterative. Since G is bounded between 0 and 2, because of the way that we defined it, we already know the regions which we need to solve for. So By the region you need to solve for, I mean at equal intervals along the y-axis. We evaluate G at candidate alphas and iteratively update the curve until the curve barely changes between iterations. Oops, too far. Using the resulting alpha values, we then construct a categorical distribution across all values of alpha, where higher weights are assigned to values with lower model accuracies. So with this, we want to strengthen the model against the harder augmentations, but we also don't want to lose performance on the easy augmentations. And we compute sensitivity during training for both photometric and geometric augmentations. And photometric augmentations are shown here. And these are some examples of the geometric augmentations. Just for reference, some of the other benchmarks that we compared to use a different set of augmentation operations. So for the experiments, we match those sets of augmentation operations when we compare across methods. So our results show improved performance on segmentation metrics in adverse weather scenarios when we train on clean cityscapes data and then evaluate on adverse weather. So this is the performance enumerated across different adverse weather scenarios, and none of these scenarios are seen during training. So we compare our work to several other augmentation approaches, some with randomized approaches like RandAug and TrivialAug, and some with policy-driven approaches like AutoAugment and IDVH. And here's a qualitative comparison between our work in AugMix and AutoAugment on rainy weather sample that fails drastically for the other two methods. AugMix is randomized and AutoAugment is policy-based, or I think AugMix uses some policy, but mostly randomized. Pretty obviously is the failure to segment the bus pixels. And at the same time, you can see that most of the sky is classified as building pixels. And we also tested this on other domains like organ segmentation. In this example, we synthetically produced JPEG compression noise and then tested our method versus the next best method. So yeah, you can see there that in the red box. And here's another example for motion blur. So this slide, oh, sorry, here's another example for motion blur. So here you can see that for the left kidney, TrivialAug actually misses classification on the left kidney there. So this slide concludes the overview on our work done so far. And I'm going to do a quick overview on what's been accomplished at this point. So far, we've gone over 4 completed works and 1 ongoing work. So first, we integrated differentiable traffic sim and end-to-end autonomous driving frameworks. And then second, we derived and applied approximations for time integration of the bicycle model for probabilistic trajectory forecasting. Third, we designed and conducted human factors user studies to investigate driving style and how it can be observed in risky scenarios. And fourth, we proposed a fast estimation of model sensitivity to account for edge cases that are not a result of traffic state. And currently, we're wrapping up work on how driving style can be extracted as a latent variable. So this is where we stand right now in terms of the research roadmap. We're at this last part here, rendering generated novel behavior, which I have planned for to work on this summer. This is, yeah. So the last objective brings everything together in a full circle, which links the high-level traffic sim and the first-person sensor observations on the road. And our work in driving style thus far operates with trajectories only. So there's an obvious gap between the outcomes of the human factors projects and the projects utilizing traffic state for autonomous driving policies. So ultimately, we want to link all of them together. And so after we generate the realistic trajectory outcomes from the work with latent variable modeling, we want to link them back to sensor observations. And this would be extremely useful for providing real-world traffic and sensor pairings, and then also would enable vehicles to detect novel scenarios from the first-person view with their sensors, despite not actually having observed them in the real world. So this would be really useful for generating synthetic data, essentially. So here's my timeline. After submission of our current latent variable modeling project, I plan to work on rendering generated novel behavior as first-person observations to close the loop between the human factor studies and the current approaches in deep learning for behavior sim. And here's a list of all publications that was completed thus far in graduate studies. And everything highlighted in yellow were publications relevant to or mentioned in this presentation. And here's a reading list of works that will be useful for the remaining work in my timeline. So with the last work and the current latent variable modeling, I'll be looking heavily at traffic sim and behavior generalization, parameter efficient multitask learning, and scene rendering and diffusion. So that is the end of the presentation. I want to open the floor for questions. Open the floor for questions. Dinesh? We could ask public questions first, and we just go back and forth.
So I would say let the audience ask the question first. I can ask later on. Let the audience go first.
I tried audience, but it seems a little shy. Yeah. Yeah. Yes. Yes. Mm-hmm. Yeah, so this is kind of, this work is challenging. So just if I can repeat your question. So in this particular results, the style 0 and style 1 don't really have that much difference in terms of outcomes. The main difference is within the third style. So without ground truth in these examples, how do we ensure that there's some sort of non-trivial difference between the first two styles? Okay, so my answer for that is that this work is challenging precisely because we're trying to do some latent variable modeling without knowing exactly how to evaluate the quality of the latent variable. So that's why we're starting with qualitative observation or qualitative results first. But another important thing to note is that for these preliminary results, we choose to model 3 distinct styles due to pre-existing knowledge from traffic psychology literature. So a lot of them do divide. There's different ways to classify people into driving styles, and one of the simplest ones is into 3. So the 3 being conservative drivers, normal drivers, and then aggressive drivers. So that's also where our prior comes from when we do the latent variable modeling. Is the prior in the Bayes. I'm last right now in Bayes. The prior is taken from traffic psychology literature and the distribution of conservative, average, and aggressive drivers. But we don't exactly enforce, for example, one to be aggressive and one to be conservative and one to be moderate. We're just providing this prior and seeing what it learns. So just providing this, even though in the literature, like the style 2 with 0.1 probability, even though that is associated with driving, aggressive driving in the literature, we don't actually enforce it in the model. So that's why this result is kind of interesting in that it kind of learns this aggressive behavior on its own. However, if we don't see any notable difference between 1 and 2, that could indicate that, for example, in our particular data set, we don't really need 3 different buckets to bin our samples into. So it could be that there's only 2 buckets of driving behavior, and one is just the extreme case and one is the non-extreme case. It could be that, there's just not enough variation in the data to represent 3 different buckets. But again, this is really hard to evaluate, which is why that's part of the challenge of the project. So.
Those are argue that's perceptible and that's not perceptible.
Yes.
So you could have 3 buckets.
Yeah.
Conservative and normal and aggressive. But perhaps the differences between conservative and normal are not so perceptible.
Yeah, exactly. So that's why the quantitative metrics will also come in handy. So we measure velocity and speed over time and stuff like that. We'll be able to perceive more of the minute differences with numbers. Yes. Yes. Yeah, so the baseline is the simulator which we use from the first work. The first work is so there was a software release called Driver, which was a Carla wrapper. So essentially what this did is it had virtual reality integration on top of the Carla driving sim. The Carla driving sim's original purpose was for actually just like training driving policies in simulation. It really wasn't intended for like as a front-facing software for like user interaction. But Driver essentially just puts this VR wrapper over it and enables it to be used for like user studies and stuff like that. So that's why we use it in the first study, just because of it was available in open source. We gave it a try, but not to a fault of Driver itself, but more on like the heaviness of Carla. There's also limited processing power in like the VR headsets, even if you have a really nice one. And so I think the heaviness of Carla itself, because it wasn't even made in the first place to be loaded onto a headset, it produced like very low frame rates, very unrealistic rendering, and it had a lot of limitations with respect to the quality. So yeah. Yeah, so a lot of things of the optimizations really aren't. A lot of these optimizations aren't even necessarily on the side of that we had to implement them even. It's more so that Carla comes loaded with a bunch of these features that are used for data collection and learning policies that we don't need, but we also can't exactly turn them off. So for example, the engine just ran extremely slowly, and even just implementing our own in Unity, the sheer fact that we have implemented our own is already like one optimization. We don't need these other features from Carla that previously lowered the frame rate. Some other optimizations that we had were, so one thing was a co-simulation between this simulator and Sumo. So similarly with the first work was extremely slow because it was bottlenecked by Carla. In this work, we have control over the density of vehicles, so we don't have to render the vehicles that are super far away from us. But also, it's somewhat of a much lighter game, basically, than Carla was. So it's much easier to send information back and forth to the VR headset, and just implementing our own gave us tons of flexibility. Does that help? Oh, is the rendering quality downgraded? So actually we noticed that so realism is definitely a challenge in VR. The assets that we use, as you can see, aren't incredibly like realistic in the sense that they look like the real world. But I think a lot of the realism comes from like the higher frame rate and the actual feeling of immersion. So it's hard to say whether the realism comes from the actual rendering or just like I guess downgrading like the rendering settings or the assets. But I think a lot of the improvement comes from higher frame rates, essentially. That also mitigated a lot of simulator sickness. Yeah. Yeah. Oh yeah, so if I can elaborate on this.
It's gonna be the traverse.
Yeah. I would like to, so basically what the human factors projects produces, at least in our current latent variable modeling project, it produces high-level traffic states like the one on the left here. This is just a visualization. It's not necessarily like what it actually produces, but if you can imagine it as just kind of like a set of positions with the road network information, it's not really like from the standard driving sim view. The output of those models are essentially just a series of positions within some road network. So we want to kind of like bring it back to observations from like sensors through maybe like diffusion. I haven't decided yet on what paradigm it could be, but diffusion is one aspect. But the idea is like if we can, so right now what we have is, I think the Waymo dataset has pairings between traffic's directories and the actual dashcam information and sensors. So the, what do you call it? The scenario ID between the perception dataset and the motion dataset, you can actually link them. So we have this really, really large dataset with pairings between the traffic state and the actual, what do you call it? First person view. But the missing link in that one is the driving style annotations. So what we can learn from large data sets just through learning is the mapping between, for example, traffic state and the first person view. So we can, for example, control some sort of diffusion model to output information given a traffic state that we want to simulate. So let's say we want to simulate like a specific intersection scenario where there's one car here and one car there. We can provide this as a condition on the diffusion output to generate some sort of dashcam view where this is the case. But what we want to do is take our human factors modeling and be able to generate different outputs in the same trajectory format as the data set. So if we can provide novel scenarios, which are realistic human driving behavior, and we can, for example, we can take a real world log and generate hypothetical outcomes with different driving styles, we can then generate synthetic, realistic looking data controlled on those sorts of outcomes. So it's kind of like linking together the
So think of it is the simulated the traffic will then drive, will provide a constraint to the rendering of the dash view. And one possibility is we're definitely exploring diffusion. And we could use these simulated traffic one rendered in the style of which we keep on building. And then you can use one. Now you're going from a single view images from the dash pane to actually video generation, which I'm sure I won't know exactly what I'm talking about because we have video story generation, which is driven by text. But now there's no reason why it's limited to text. You can also use to using traffic state of all the nearby people because every single one of these state corresponds to this. So it's not only constraints that will actually constrain the diffusion rate or the diffusion basically. Make sense? Yeah. That's what I'm talking about because that's what I'm thinking.
Yeah. And I think this is feasible because there's already a very large data set, like the perception and motion data set from Waymo give us a lot of pairings between traffic state and dashcam view. So we can, I do believe that we can learn some sort of like reasonable mapping or generalized mapping. But the novelty will come in from the actual behavior modeling where we generate different realistic outcomes. We can see how those realistic outcomes manifest from like the first person. So that'll be like one interesting aspect.
Although there with the very fact that these traffic stable actions provide constraint into diffusion rate video generation.
Yeah. Basically, like kind of like control net, but like with traffic states.
Yes.
Yeah.
First of its kind.
Yeah. Yeah, basically. So that's the plan for the summer. Any other questions?
Laura, can you hear me?
Yes.
So, you're talking a lot about this traffic kind of thing. So you have, if I look at your this 4 or 5 different projects you show, or 5 or 6,
Yeah.
so you have a lot of data. You look simulators like, Game Simulator Unity.
Mhm.
And then you also have this data where you guys have been gathering with your own like a simulator in our lab, human driving, but in a simulator.
Yeah.
So, there's a pure synthetic data from Unity like Games Engine. Then there are kind of driving simulator, but human drivers, what you guys have done, very impressive stuff. But you have worked at Waymo, right? And you mentioned all about how people in DC are spending so many hours this thing. Is there
Mhm.
any way you get access to real world behavior data? Because the real world, and simulation is simulation.
Yeah.
And there are a lot of data sets coming up, but I wonder if anybody has a large scale data, and people have a lot of videos and LiDAR data.
Mhm.
Can you extract behavior from them? Is it possible and use that, something like that?
Yeah. So if I can rephrase your question, you're basically wondering if there's a way to get large scale driving style annotations in the real world. Because we have, like, for example, these simulators which extract behavior from with user studies. But then we also have like these large data sets from companies like Waymo, which give us a ton of trajectory data. So I guess the question
Right.
is your question, just to confirm, it's kind of like, can we somehow get our hands on style annotated data in the real world? And
Especially, and I would say you're right, but we self-generated behavior data, becoming a lot of focus on behaviors.
yes.
They give trajectory and LiDAR and video. So can we somehow generate or get access to real world behavior data? And if so, how will the results change in that case?
Yeah, so I would say like that part is extremely difficult. I'm not sure if it exists, is the real world behavior annotations. We do have access to massive amounts of like just like pure trajectory information, but we don't have any information on their driving style or whether someone's like more of a passive or aggressive driver. We don't have any information around that. So that's kind of what the latent variable modeling approach is doing, is seeing, we don't have those annotations, but can we learn some sort of style that's like dormant within this data, even though we don't have?
So is it actually, Laura, it came back, and originally I was thinking Ganesh's question is no, but now I think to think of it, maybe. So Ganesh, I'm not sure if you understood what the difficulty is. Because what we were trying to do is you could actually easily extract trajectory data and track it over time in video, and there are lots and lots of camera on the road. So those data are widely available, and not to mention that there is also all these autonomous vehicle driving, hundreds and hundreds of miles, a million miles, 100 million miles, and collecting data. The problem there that Laura was trying to say is the annotation, automatic annotation of the driving style associated with the trajectory. And the style, because we currently are relying on human personality survey.
Yeah.
And that's how we get it automatically annotated style, the driving style with the trajectory. But perhaps we don't really care what personality they are. Perhaps all we care is just the kind of style, the driving style, which will still be okay. You might still be able to do.
Yeah, it's possible that, are you saying?
You don't care who's behind those wheels. All you care is consistency of the driving crazy drivers, or really slow driver, grandma driver, extremely slow. And you don't care about personality. You just be able to extract this. And the trajectory data includes all your views. It may not be adequately fine enough.
Yeah,
because all we are observing in the camera position. We don't know the velocity, we don't know the acceleration.
Yeah, and I think like that's also one thing that we can explore with the latent variable modeling.
Yeah.
Like you mentioned, the buckets that we end up learning with the latent variable may not even necessarily correlate to just driving style.
That's right.
We assume in this work that, like, if we account for context and intent, that the remaining variation is from driving style. That's a very simplified way of putting it. So we think that it's driving style. but it could be something else entirely. So that's another challenge of this latent variable modeling is even though we know what we want the variable modeling, it may not necessarily model what we want it to. Yeah, I think that's a really interesting point. And we can also see like one way of validating this as well is if we were to infer the ground truth or most probable driving style for each sample and then evaluate it on the benchmarks, it should be additional information to help improve the accuracy of those predictions as well. So it is like a factor that we want to maintain across time. It's like a temporally consistent variable that might help us keep the consistency between previous and future actions. So for example, if history is consistently a conservative driver or passive driver, then the future output should also hopefully be likely to be passive outcomes as well.
Dinesh, does that answer your question?
Yeah, so that's fine. So I understand the challenges here, So one question would be, and if eventually you take this ideas to real world traffic, how realistic would it be? I understand the challenge of getting real world behavior data. And so how do we validate, and it's not a question, I guess, maybe Waymo can do it someday. But do you have any ideas to do better validation given this challenge of getting good real world data?
Yeah, so one thing that we can do, so if we don't have access to real world data on driving style annotations, one thing that we can try is between the two approaches for modeling driving style. So we have on one hand, we have the user study style where we just query the users directly. On the other hand, we also have the latent variable that we're modeling. And the latent variable that we're modeling and the MDSI have the driving style survey have no relation whatsoever. So one thing that we can do to validate it is cross-check it. Because the MDSI has been used for so long in traffic psychology, it's a whole different world of research. They have published tons of distributions of, like, for example, MDSI distributions among the population. And if we can find some meaningful relationship between the extracted driving style, which is a latent variable, and the MDSI classification, this might be a much more robust way to validate the actual latent variable itself. And also, it's probably a much more direct mapping between the MDSI and trajectory data compared to the linear correlation analysis we did before with like braking and throttle and whatnot, because variable and how it correlates to driving psychology literature from what they've measured in the past 2 decades. So that's one way that we can validate it on a large scale. Does that help answer your question? That's what I was thinking.
Yeah, sort of. You're in the right direction. I can see that. As I said, given the challenges, I don't know what the best fit. There's no clear answer, but I guess if you can address in any way, that'll be great.
You should probably mention that we also did a correlations on the MDSI personality classification and all these different measurements that we have to get, like the acceleration.
Oh, yeah.
velocity, and there was a correlation.
Yeah.
Right, and we did find the more aggressive driver
Mhm.
tend to accelerate much more abruptly.
Yeah.
Right, so
Yeah.
those are a correlation because personality classification indicate they were aggressive
Mhm.
and or they are passive. And it reflects in how they, in their acceleration.
Yeah. So, Professor, so basically, like what we've done recently, which actually under submission for right now, is we conducted an analysis between so actually there was prior work by Aniket on trying to relate driving style to different trajectory phenotypes. But so this study that Aniket was a part of essentially looked at mapping trajectory phenotypes to like their own version of driving style behavior. And this was very useful and very detailed, except that the scenario that was examined was a very specific highway lane change scenario. So conversely to our project, which essentially surveys an individual person's driving style and has them drive through a scenario, The study by Anikit essentially took a bunch of users, put them as an observer in a simulation, and then had them classify others. So this is the other direction, is how your driving style is perceived by others. And I can imagine that if, for example, we want to deploy this large scale, naturally the extension would be generalizing Anikit's work to a much larger distribution of scenarios, because that one was strictly within like a dense highway scenario. But if we, for example, we wanted to observe driving style at a large scale from observations, that's what I would imagine if we wanted to, for example, just like take a vehicle out on the road and then start classifying different vehicles on the road as driving styles. That's how I would imagine is kind of like a link between our work and his work in scaling in different up in the diversity of scenarios.
Okay, actually, I know Aniket's work. He was at UMD, and in fact, there's a follow-on work by Rohan and Ding.
Yeah.
But in all those work, it was synthetically generated. So even they did not have the act problem real world data. So that they are the same problem that we are all dealing with. The follow-on paper I put in a chat window. They didn't have real data to validate it. They're the same issues there.
Yeah. And the same thing with the behavior phenotype, using observed trajectories to classify driving styles. That one was also observed in simulation as well. So it wasn't real world. It was a controlled simulation.
Agreed.
One might argue that whether it's simulated or observed, it doesn't matter because it's our perception of what we observe.
Yeah.
Right. And we don't even know what their intents are. This is all about perceived driving style. And in fact, one might argue the perceived driving style is all we need because it's what any vehicle will see. Because at the end of the day, we don't know exactly what the person is, aggressive or conservative. It's how we react to aggression and conservatism.
Yeah, I would say the sim to real gap in Anikit's work is definitely like Professor Lim mentioned. I think that it's less of a hump in terms of sim to real gap compared to like a robotics task for sim to real, because my personal assumption is that humans are pretty good at processing the sim to real gap. So if you were to say, for example, like treat this simulation as if you were seeing it in the real world, I would imagine humans are pretty good at that. So I think perception of other driving styles is probably more robust than like learning from different driving styles in simulated data and then having a machine or network interpret it. Yeah.
Dennis, you have any more questions?
Nope. Maybe I think, Laura, when you go to Waymo, figure out how to solve it there, get the data from there.
Okay.
That's why they want her.
Yeah.
They wanted her, they want her done a year before she graduates.
Yeah.
I'm okay.
Last summer, yeah. Hello? Yeah. Okay. Thank you.
Out of curiosity, what else do you find that humans roughly you can create a simulated driver?
Yeah.
People work on self-driving cars. Say that they're big differences. Any sort of robotic data.
Yeah.
Do you find that there are systematic the kind of agency?
Yeah, so one thing that you'll notice if you like just from the pure acceleration perspective with TRPO, if you were to learn an optimal acceleration agent versus having like a human accelerate, it's super obvious that the acceleration agent can produce like massive amounts of jerk, like just like high rates of change with brake and throttle. And this might be optimal for like the actual reward, but it may not actually be realistic or comfortable for the rider in that sense. So surprisingly, like in commercial products, people end up using like more like imitation learning or model predictive control approaches rather than reinforcement learning. But I know that there is some really interesting current work going on with like large scale reinforcement learning. And I think what they're doing is they're trying to use some combination of imitation learning and reinforcement learning to kind of like scale up like reinforcement approaches there, but then maintain realism from real world data. So I know it's a thing. But again, at the same time, to make that simulation closed loop, you definitely need like those traffic models could be differentiable if you want to use them in some, for example, some like novel scenario generation. I know like previously there was like a large difference, but what I'm trying to say here is that it's kind of interesting. Like I think recent work is trying to close that gap basically. And a lot of the challenges were with like software and hardware. So a lot of the time, like I mentioned before, a big hump that like we have to cross with these works in terms of like RL is simulation speed. So I think a lot of the recent works deal with actually engineering like these super fast simulators to run at like 1,000,000 FPS.
Like Genesis.
Yeah, basically. Like it is just like the simulation speed is the thing. Yeah. So I think now that like these systems are becoming a thing, I can imagine that like the gap between reinforcement learning and imitation learning approaches will be closing. But as of like right now, I think there is a huge difference with like it's very robotic and very like optimized, like in terms of the optimal policy may not be the most comfortable one for a user. Or yeah. And that would also make it much harder for mixed autonomy because other people because in our experiments with mixed autonomy, we assume that like the human drivers will react to the AV as if it were a human, but we don't know if this is actually the case. It could be that if a driver seems overly robotic, we don't know how people are going to react to that. So that's also like an open-ended like research area. However, it's a very futuristic one because we don't really have mixed autonomy systems yet, at least in Maryland. Like you might find it in the Bay, but not here. Also, it'll be different in the Bay versus like West Virginia, because people in the Bay probably know about autonomous driving. Yeah, they're completely different populations. So I imagine like the like human to robot interaction will be more of a thing like once that stuff scales up. Yeah.
Okay, you guys have any more questions? If not, we're gonna have to.
I'm gonna